The time has started, right? The time has started. Right.
Yeah, please challenge the report.
I would like to challenge number 9, which is magnetic resistance.
Number 9. Accept or reject. We accept. Accept. Please write the name of your presenter. Reporter, you may start when you are ready.
Hello everyone, I'm Chen Yuan from Tinhan Bromeda. Today I'm going to report problem number 9, magnetic assist. Here is the problem statement. Attach one or two magnets to a non-magnetic non-conductive base such that they attract the magnet suspended from a screw. Investigate how the motion of the moving magnets depends on relevant parameters. In this experiment, we mainly focus on how this gas reflects in this experiment and the classification of different conditions of the magnets. Firstly, let's start from the observation. So in the left side is the attractive one. So from this video, we can see that the suspended magnet accelerates toward the magnet and will finally stop above the magnet. And the right side is the repulsive one. So in this video, we can see that the suspended magnet accelerates away from the magnet, and we couldn't know why. We couldn't know which point does the suspended magnet stop. And then it's an outline of the presentation. So the main concept in my presentation is around chaos. There are 3 conditions for chaos. First one is nonlinear, and second one is sensitive to initial condition, and third one is a long-term unpredictability. So in my presentation, I will demonstrate 2 different simulations to have a better investigate of this phenomenon. And for the data, you can see that I do 6 different parameters, 6 different experiments, and finally do the classification of them. First is the simulation. So we call the suspended magnet as Bob, and here is the first analysis of it. So from this graph, we can know that there is totally 4 forces exerted on the Bob. First one is the gravity, and the second one is the rope tension, and third one is the air resistance, and fourth one is the magnetic force that caused by the magnetic A and magnet A and magnet B. So the way that we calculate the magnetic force is that we first measure the magnetic field of a magnet and calculate the magnetic moment and magnetic charge of it, and use this equation to calculate. So the resultant force is the combination of the force 1, 2, 3, and 4. So how do we know? How do we model the position of the Bob at a single time? Is that we assume the delta t is approaching 0, so the force is fixed. So it will do the constant acceleration motion. And then the other modeling is the potential energy of the Bob. So if we imagine the Bob as a ball and use this potential energy equation, and then we can get this graph. So if we compare this and that, we can know that the lowest point of the potential energy is that the position of the magnet and also the stable balance point. And then it's our experiment setup. So as you can see that I fixed the string on the ceiling and use a really long string to ignore the displacement in the z-axis. And also it's the way that we release the Bob, and this is the coordinate. And here is the measurement of the magnetic field. So first, I'm going to talk about the experiment data of the repulsive one. So here, as you can see that I put 1 magnet on the plane, and the blue dot represents the magnet. So I do 2 different trajectory. That the first one is the coordinate of the initial position of the Bob. One is this, and one is that. So, and here is the potential energy graph. So we can know that if it's 3 conditions for chaos, so we can know it's chaos. And then we change the magnet that puts on the plane. This time we put 2 magnets on the plane, but the 2 magnets, the distance between the 2 magnets are really close, which is the 5 centimeters. So as you can see that we can see the 2 magnets as a big magnet, since that the 2 magnets are put really close to each other. And also we can know that it fits 3 conditions for chaos. And then how about we put the 2 magnets far away to each other? From the potential energy graph, we can know that there are 2 different hills of the potential energy, and it also fit the conditions for the test. So if we're just modeling, we didn't know that if it's really happened in the reality world. So we do the experiment by the experiment setup that I have just mentioned in the previous slide. So there is also some discussing point that there is some interesting point that we can discuss is that if you look at the range between this, we can know that because the magnetic field is weaker here, and because we can see that these two magnets has one magnet, so the magnetic field will be bigger. So this is close and this is far. And we also can find that the trajectory here is not the same as the simulation. And here I'm giving a possible explanation for it, is that in the simulation we use a magnetic charge, but in reality the magnet has volume, so the bob's motion is flat. And then let's give it a quick summary. So we can know that the calculation for the magnetic force represents not linear, and the trajectory difference represents the sensitive to initial condition, and lack of stable balance point represents the long-term unpredictability. So we can know that it's cast. And then is the experiment data for the attractive one. So just as the same as the repulsive one, I put one magnet here. And here is the potential energy graph. And we can, from this potential energy graph, we can know that it's only have a single stable balance point. So it's cast. Let me talk about it later. And then is that we put the two magnets, and the two magnets are close to each other. And as you can see that because the two magnets can be seen as a single big magnet, so we can say that it's only a stable balance point. And then is the two magnets, but the two magnets are far away to each other. So as you can see that in the here there is a set of points, which means that if the bob just pass through the set of points, the trajectory may bifurcate. And you can see that there is two stable balance points. One is here and one is here. And also is the experiment data. We can know that the trend of it is really fitted modeling, and we can know that this and this have a single stable balance point. But if the magnets are far away to each other, it has two stable balance points. So the magnet might stop on here or here. And also the quick summary of it. So the calculation for the magnetic force represents the non-linear, and the trajectory difference represents the sensitive to the initial condition. And more than one stable balance point represent long-term unpredictability. And in my experiment, we can know that these two conditions fit these two conditions, but it didn't fit this. So can we call it cast? We don't know. So I give it another term called transient cast, which means that it just fits part of the conditions for cast. And we can know that that condition is cast. And then it's a comparison between the attractive and the repulsive. So this time I put the bob at the middle of the two magnets, and the way that I quantify the cast degree is that I calculate the angle between the V1 and V2. This V1 and V2 represent the two different trajectories. And we can know that because the repulsive one appears cast more early, so the cast degree we can say that is repulsive is bigger than the attractive. And then is the discussion. So in the discussion part, I want to discuss the effects of damping, because that we know that in reality the bob will be affected by the air resistance. So I think that's a really important for the damping. And also I compare the angle between the V1 and V2. So there's no doubt that if the damping is really big, energy will quickly just disappear. So the cast degree is not that big. But there's a really interesting point that we can know the small amount of damping caused chaos earlier because that this is you can see that the green part is the 0.001, but the red part represents 0. So that there is two possible explanation for it. Is that first one is small damping enhanced sensitivity, and the second one is that maybe a small amount of damping will allow the bulb to easier to stop near the setup point. And then is the discussion of the more magnets, because the problem statement just mentioned 1 or 2 magnets, but didn't mention more magnets. So I really want to know that what will happen if we add more magnets on the pen. So my prediction is that if the number of the magnets increase, the unpredictability will also increase, then the chaos degree will also increase. And then it is the conclusion. In my experiments, we can know that there are 3 conditions that fit chaos. First one is sensitivity to initial conditions, and second one is long-term unpredictability, and the third one is nonlinear and complex equation. So we can know that. So we can know that if it fit all the conditions, then it's chaos. But if it fit part of the conditions, it's transient chaos. And then we can know that in my experiment, I have classified different conditions of the magnets to chaos, and we can know that the repulsive one, chaos degree is repulsive one is bigger than attractive one. And that's all for my presentation. Thank you for attention.
Question of the opponent to the reporter.
Okay, then the first question is the decay of the distance between the fixed magnets and hanging magnets to damping motion?
Sorry, can you repeat again?
It's the decay of the distance between the fixed magnets and the hanging magnet which eliminated bulb at damping motion.
Yes, if it attractive, then it will just.
Yes. And is it a constant acceleration movement, as you have said? Is it a constant acceleration?
Oh no.
So will the number of the magnet influence the movement of the bulb?
Yes, of course.
Did you define the chaotic movement in another way?
What do you mean by movement?
Oh, never mind. Do you guys use a Gauss method? Do you guys use the Lyapunov stability?
No, I didn't use that because I think that's not fit this condition.
Okay. So, as your presentation has shown, there are several lines that are overlaying together. So, if overlaying the lines together and it is similar, well, that means that the movement is not the chaos movement.
It depends on how do we define similar.
So, are the geomagnets considered in this experience?
I didn't consider geomagnetism because we use modeling, so we didn't consider it.
Okay. So you use most of the experience is simulated, right?
Yes.
Okay, that's
就应该是2.1，不是它的那一种，然后比较出来这个造成这些大的就麻烦一点，还是一直洗，就跟我们大概第3个是类似的，可以提跟是可以提出一下，是一个 this application magnets may not right. This application of magnets may not
Please take the floor.
Greetings, honorable judge and participants. I'm going to have a roughly introduce of the magnetic system from TYPT S503. Now the problem statement, just look at queries. And the reporter have said their key point is how does scale reflect in the experience and classification of it. Now, this is an overview of the reports. The theory parts. First of all, chaos is the mainly focus, the main focus that the reporters is on. And they use program to divide the potential energy and visualize equilibrium, like the 3D grid. And their experiment parts, they investigate the stable points in the magnetic field by analyzing the potential energy. And they use program to divide the potential energy and visualize equilibrium that I have said from the theory. And investigate the effects of damping to the chaos, which is known as the distance from the fixed magnets to bottom. And the conclusion parts, they calculate of magnet first, and it is not a linear function. And the single or more stable points. The longer term is unpredictable, like they have shown on the presentation. And they add more magnets in the future. That is their prediction, and their prediction will be shown on the presentation too. And they didn't talk about the theory and experiments is connecting to each other. Now there are some remarks to the reporters. There's an advantage that they provide a lot of graphs that is pretty clear. It is very clearly that it can show the whole experience. And they have a completely theoretical models that can explain this chaos. But there is a suggestion that some of them are not clear enough because of the word is not visible from this place. So I think that you can make it bigger. Yeah, that's it. And I want to go into the discussion part. Okay. First of all, that we have found. Please turn to the page that will show your. I think it's page 17.
Just wait a minute.
Nice.
Here?
Yes. Can you show the motion of it? Maybe they did it run for a while. As you can see, the period of it will go out and goes in again. The period is getting it is lesser. They have to decrease on the period. So as you have said that it might be the damping motion, right?
The damping motion.
Yeah, it might be, right?
Right.
So if it is a damping motion, then what causes this damping motion?
I would say that is because that this magnet will give this magnet a repulsive force. So when it goes here, then affected by it, so it will go here, and then because it will affect by the gravity, not gravity, the rope tension, so it will finally have the force to come to the original place. So it will go back again and repel again.
Yes. So every time when it moves to the end of this motion, will it be the same way they come here and they will go back in the same way?
It depends on whether it's really exactly the same or a little bit different, because this is chaos, so if there is a little difference, the trajectory will be different.
Okay, now I want to go to the page 4. The video one. Please play it. As you have shown that the initial placement of the magnets is different, so it is just a demonstration, or you
It's
do
just
it?
a demonstration.
Okay, it is just a demonstration. Now, I think it is, we have talked about, please go to the 3D graph. I think it's about 21 minutes. This one? With 2 magnets, yes, exactly. As you have said that if the magnet is too far away of these 2 magnets, then you won't be affected by the force that is caused by this magnet, right?
Again, please.
Let's say that you consider that if this magnet move far away to these 2 magnets,
Yes.
then the effect of these 2 magnets will be not visible, or it's not very obvious. So you can consider this kind of phenomenon.
If we put another magnet at a really far distance, then I think the bob won't affect by the other magnet, but it depends on how far we put it.
Yes. So did you define this?
Define.
How far it can be put to be not affected by these 2 magnets?
We didn't define it. In my experiment, I just do if the 2 magnets can be seen as one, or it just can be seen as 2. It is different because it has 2. Depends on whether it has a single balance point or 2 or more balance points.
And about the attractive parts that I've told about the oh, let me just write it. It's a Russian name. A Russian name is how to pronounce it. So yeah, it told us that there will be a circle while the middle of the circle is S0. So if things that have a motion inside here, in the end, it can be chaos. So if it is attractive, that means in the end it will be attract at the middle of it. So I think that this guy is stable. It is I think it's stability. This spin could be considered in the experiment to make it maybe more accurate than about the attractive part.
Giving some suggestion that how could I use this in my experiment?
Because as you have said, this enter the saddle part. You know what it means? Yes, it's the saddle part. Yes, the saddle part. So the saddle part in 2D it should look like this, right?
Yes.
So this at this point, the attraction from this magnetic, the force that's caused by this magnet and this magnet are the same.
I think that's not what I think, because the zero points that put in my presentation is
Yes.
like this. So
Oh, it is
the magnet, is attractive, not this is repulsive.
Oh, I
So
got it.
the zero points will be like this.
Oh, I got it. tricycle.
Yes.
So for the magnet stop in each of these
Yes.
medium. So can you give me some explanation about the chaos degree?
You here?
Yes.
Okay, the reason why I do this experiment is that I think in the previous experiment, you can see if it's a repulsive one, if we put this magnet here, just as the previous slide, we can see that it will just go like this motion. And I think that it is not affected by this magnet, so I try to put the bob like in the center, in the middle of the magnet, so that it appears more chaos properties, so that I can have a better investigation of this.
Okay. And I have a question about that. As you have shown on your experiment setup, that you do things like that, right? And this is online, and you use the matches to learn this one.
Yes.
So I think that you will have the initial velocity here, right? So do you try to control the initial velocity?
And initial velocity? No, the initial velocity is 0.
It's 0.
Yes.
So it is at the middle point of this kind of two points. Because if you cut this line, you
Oh, we did this. You mean was right in the middle of the two magnets?
I think can we show the setup of the experiment? Yes, I appreciate it. Right here.
Yes.
So, why did you put this rope here?
The reason why I use the string to release the bob is that I want to make it more accurate. Because we can't use the hand to release it.
Yeah.
Yes.
As you can see from this video, we have an initial velocity and constant.
No. It's
Oh.
not initial velocity. The initial velocity is 0, and because the force exerted on the bob, so it will give it an acceleration.
I got it. So it is, if it looks like this, then this thing will be in the middle of these two.
This graph is just a demonstration. It's not real. Yes.
Okay, got it. Then about the magnetic field problem, how do you measure it? Using the sensor, how do you use that?
Okay. I put the magnet here,
Yes.
and this is a magnetic sensor.
Yes.
Okay, so when we know the distance here, right?
Yes.
And we also got the number that is measured in the sensor.
Yes.
So from here, this is the magnetic field,
Yes.
and this all the number is that we can get.
These are the parameters that you have shown.
Yes. And we can calculate this. This is called the magnetic moment.
Yes.
Yes, and we can calculate the magnetic charge.
By this formula.
Yes, and we can distribute it into this formula so we can get the force.
Okay, got it. But as we have known, if the magnet is a circle on top of it, I can do something like this. So the magnetic field will be the strongest at the middle of this, but it will be lesser at the side. So how do you make sure that these things will not affect the whole system?
It certainly will affect that. So that's why we use the modeling to conduct our experiment.
Oh, okay, I got this. And I think that's it. Okay.
Upon that, please summarize the discussion.
In our discussion, that we talk about a lot of things such as the several parts of the, they did not define how far the magnets how far the magnets will not be influenced from these two magnets that they have shown at the table, the blackboard. And I have provided these rationalized theories that can be suitable for the attractive part of this. And second, the chaos degree is clearly shown on this, but I think that it should be to be easier to read the whole formula, and that's it.
Question of the reviewer.
For the reporter, could you go to slide 20? I wanted to ask, how do you quantify chaos? Since you mentioned qualitative descriptions, but how did you verify whether your cases were qualitative or quantitative?
You mean quantified chaos?
Yeah, since you mentioned three conditions.
Just as I have mentioned that in the I calculate the angle between V1 and V2.
Oh, okay, thank you. Could you showcase which graphs reflect your experimental data? Or just like, yeah, since I saw a lot of different simulation graphs and I wasn't sure which slides did you showcase the trajectory as experimentally shown.
Which graph do you want?
Just one that showcases your experiment.
Yes, like this?
Uh,
Experiment?
Yes,
You
sure.
mean real
Yeah,
experiment
Yeah,
data?
the real experiment data.
No. Here.
Oh, okay, so that's the real experiment. Thank you. For 25, can you go to slide 25? Since you mentioned that there was the potential energy field, in your experiments, did you see evidence of two equilibrium positions?
Yes.
Yes, okay. Could you go to slide 29? Did your simulation include air resistance inside?
Yes. That's why I changed.
Oh, okay, so you changed it after you saw the resistance, correct?
No, I changed the coefficient of damping.
Oh, okay, so you tuned it. Okay. And could you go to slide 27? Is this like a simulation or experiment?
Simulation.
Okay. Question to both the opponent and the reviewer. What force do you think causes damping in the repulsive scenario?
Causes damping?
Yeah, actually.
Okay. I think the air resistance causes the damping and some energy decay from the attractive magnets that cause two ball.
Yes, I agree with the
Okay. Another question to both. I think you mentioned that you were talking about at what point is the magnet too far away from the pendulum for it to matter. Do you believe this is relevant to the phenomenon?
I think that if the distance might influence the whole experience because while the distance is far away from the magnets, that might the fixed magnet might not influence the magnet that is.
Yes, definitely. The distance between the two magnets depends on the chaos degrees.
Okay, thank you. Also, could you clarify what your definition of reductive the condition is for chaos?
Oh no, I just mentioned that to emphasize that the attractive magnet, attractive part of the experience might have been.
Oh, time's up. Reviewer, you have 2 minutes to prepare your report. please take the floor.
Hello, my name is Ethan Hu from Team Donors, and I'll be reviewing problem number 9, magnetic assist. So the main focus of the reporter in their experiment was how is chaos reflected in this phenomenon, and also how you can classify different conditions of the magnet. So the reporter's performance. Here's what the reporter did. First of all, they split the phenomenon into the attractive and repulsive cases, along with the single magnet and double magnet cases, and analyzed those cases separately. For the theory, they had two pretty distinct theories. First of all, they created a simulation using 4 forces: gravitational, tension, air resistance, and magnetic field. Additionally, they also calculated the potential energy due to the magnetic field at different points along the possible movement of the pendulum, and they predicted whether or not the equilibrium points would end at a single point or 2 points, depending on the field. For the experiment, they had 2 different types of experiments. They mainly used simulation using their force calculation to try to look at different cases and see whether or not in the simulation the phenomenon acted chaotic. While they also had an experimental case where they tied a bob to a string, cut it, and let it move to predict the movement. In terms of pros, they had a lot of clear visuals. The graphs were really informative, along with a clear derivation of how they got their forces and their energy equation. Additionally, they gave a really logical sequence of their presentation, and they had a really powerful simulation. However, in terms of cons, their qualitative to quantitative definition of chaos wasn't that clear, and also many of their experiments were simulations, so we believe that that was a little bit of a con. Next one. In terms of the opponent, they did 2 main things. First of all, they talked about the theory to the experiment connection, so they clarified some of those. And they also brought up their own point of the Lyapunov definition of chaos, which they said for the attractive scenario is something that the reporter should consider. In terms of pros, they had a clear, well-placed voice, and they had good time management throughout their discussion. However, for cons, their definition of Lyapunov was slightly unclear. Next slide. So for the first discussion point, the opponent pointed out that there was a damping motion in one of the graphs. The opponent asked what the repulsive force was, while the reporter had some explanation of the repulsion. I later asked to clarify, and they both said that it was due to the air resistance, which we agree with. The second discussion point was the distance of the magnet. This one I found slightly unclear, so the opponent asked at what distance do the magnets stop influencing each other, and I thought it was slightly unclear because I wasn't sure whether they were talking about the pendulum bob versus the magnets. However, the reporter said that they were talking about the fixed magnets positioned next to each other and how they interacted as 1 or 2 magnets. I found that the reporter's explanation was pretty clear, and asked to clarify later on. Third discussion point was Lyapunov stability. The opponent mentioned that for the attractive case, this could be used. The reporter said that they didn't really utilize it because they directly used the potential energy field, and they asked for clarification on the use case. Next slide. Then they discussed the bob in the center. The opponent was talking about whether the initial velocity was truly 0. However, the reporter said it wasn't really an issue. First of all, because this was a simulation, so they could control that. And second, because when you release the bob and you cut it, you don't put any external force onto it. Next slide. And then they clarified the calculation. Next slide. And then one point that I believe they missed is they didn't really talk about the tension of the string, because while they included the force that varied depending on how far the string was stretched, they didn't really talk about the slack scenario.
Concluding remark.
Okay, thanks for the opponent and reviewer. I'm going to do the concluding remark. So first part is why don't we use the Lyapunov exponent to prove the chaos? So let me explain it. So if the maximum Lyapunov exponent is bigger than 0, then it will be chaos. So the equation is like that. So I think that this equation is just use the if the two trajectory is really close to each other in the initial condition, then it will bifurcate over time. So I think in that way we can use this. And we have also discussed about the distance between the two magnets below will affect the result or not. I think the distance will definitely affect the characteristic, just as I have said that if we put two magnets together, it can be seen as a big magnet. And if we put two magnets far away, it has two stable balance points. And the reason why I define the cast as three condition, if it fits all the condition, then it would be cast. If it just fit part of the condition, it would be transient cast. Is that first I've tried to put two trajectory of the experiment data together, and we found that we couldn't define what is little difference in the initial condition. So that's why I use the modeling to like control the initial difference in my experiment. And yeah, that's all. Thank you.
Okay, now is the question from the jury. Any questions or comments?
You instead of using two magnetic sparks, you just use one. Can you observe the volume below?
If we just put one magnet below, we can see that the trajectory will be different over time, but it will finally get to the point, get to a single point. So we define it as a transient cast, which means that part of it is cast, but it's not cast at all.
Your opinion?
I think I agree with them based on their three definition chaos. With the single case, you still see a really easy deviation based on initial conditions. However, in the attractive scenario, the final equilibrium positions will be clear.
They could provided a very clarified 3D grid of the attraction of the magnet. So I think that I agree with the opponent and the reporter's idea.
Any more comments or questions? Yes, please.
Can you bring your theoretical model on the screen?
I'm sorry, just wait for a second. Is it here?
That is one.
Oh, that's next.
The one you have magnetic charge. Okay, here.
Yes.
All right, question for Greenwood. So they measure the magnetic moment and define magnetic charge. So does this make sense to you? Okay, does this make sense to you, starting from the opponent?
Can you repeat the question again?
So he defined very bottom one, right? Magnetic charge moment, yeah, equal to QL. Q times L. So does this make sense to you?
Kind of makes sense, but I think there should be some clarifier about the formula.
Okay, about the reviewer.
Honestly, I would rather just use magnetic dipole times magnetic field. However, it seemed close to an electric field, so I guess it still counts as a field.
Can I explain? The reason why can I use this to calculate it is that we imagine a single magnet as many coils add together, and if we really want to calculate the real number of it, we need to use the Biot-Savart law. But it's too complicated. So because in our experiment, I think if the distance between the magnets are far and the electromagnetism the effect of it is really small. So I think it's suitable for this condition.
Any more questions?
So I have a question for the opponent. You raised the question, the initial velocity of the suspended magnet
Yes.
to the reporter.
Oh, actually, I misunderstood their experimental setup.
So it should be the initial release position of the suspended magnet affect the motion, right?
Yes.
Thank you.
No more questions? Then jury, please begin your score. Okay, now it's scoring time. Show your score. 87688 for the reporter. Now next for the opponent. Okay, ready? Okay, 77676.
对了，你 double check。
Now for the reviewer. 77776. 77776.
Okay, correct.
Okay. So let's take 10 minutes break.